Okay, good morning. Okay, this is Professor David J. De Los Reyes. Okay, the date for today is October 28, 2023, and the time is 4:47 a.m. Okay, my topic for this morning will be a continuation of my topic, AC machines. We are still on the study of transformer, and this will now be lesson number 49. The topic for this morning will be another example problem of the application of the so-called SCAT connection of transformer or the TT transformer. Okay, let's proceed. The last time around, I discussed the another example or first example on the computation of currents. Okay, if the connection is SCAT transformer. Actually, the first discussion the last time around is actually the conversion from the three-phase to two-phase. Okay. The last problem was the conversion from three-phase to two-phase. And for this morning, it will be two-phase to three-phase. So this will be the topic for this morning. A problem involving the connection two-phase to three-phase, because SCAT transformer is actually got three functions. Okay, got three functions. It can convert three-phase to two-phase. It can convert two-phase to three-phase, and it can convert three-phase to maintain to three-phase. So we are done with three-phase to two-phase, right? It is actually this one, but it was the reverse. This part here is on the primary, and this part here is on the secondary. So for a two-phase to three-phase, it will be the reverse, right? So we will be discussing this one this morning. Maybe the next time around we will discuss this one. Okay, I will try to continue. The subject matter for this morning will be AC machines, lesson number 49, and the title of the topic will be example problem on SCAT transformer, that is the conversion from two-phase to three-phase. Okay, I will try to read the problem. The primaries of two transformers are connected to a 2300 two-phase source. Okay. The transformer is SCAT, so we got the so-called teaser winding and the main winding. The teaser winding is the winding that contains the 86.6% tap, and the main winding is actually the winding that contains the 50% tap. 50%. Meaning each winding on the main winding has a tap of 50%. So to be called the main winding on a SCAT, there should be 50% tap, 50% tap. Okay, I will try to continue. The primaries of the two transformers are connected to a 2300 two-phase source. Meaning to say, single phase, so it will be two-phase, right? And the connection on the secondary side will be three-phase. The one end of the teaser winding is connected at the midpoint of the so-called main winding. It is connected here, right? So if this is connected here, this is to be considered three-phase. Why three-phase? Because if we try to get the voltage across this, it should be 460. And if we try to get the measurement of the voltage across this voltage here, from this going here, it will still be 460. The third one, 460. And if we try to measure the voltage across this, it will still be 460. So if the connection on the secondary side is a letter T, that's why a T is cut or T connection, right? It is considered three-phase. Okay? It's balanced. The secondaries are connected SCAT and T and deliver a 460 volt, 130 kilowatt, three-phase, 0.866 power factor lagging load. So meaning to say with this given T connection, okay, the three-phase load connected to the three lines coming out is 130 kilowatts, power factor is 0.866, and the voltage between lines is 460. This is 460, and the two outer lines is still a 460. That's why it's a balanced three-phase load. It is considered three-phase, right? Calculate A, the current in each of the transformer winding on the primary side. On the primary side, there is the so-called primary teaser winding, primary main winding, and the problem is asking what will be the current on the teaser winding, consider the primary side, and what will be the current on the primary side, consider the main winding. So this is what we are looking for, IP and IP here, right? The configuration is something like this. This is 2300, this is 2300, right? Letter B, the current in each of the winding on the secondary side. The current on the winding on the secondary side, like what I said a while ago, for this teaser winding, it got the primary side and the secondary side. Even the main winding, it got the primary side and it got the secondary side, right? But since the load is balanced, right, the currents passing through line number 1, line number 2, and line number 3, these should be equal. So meaning to say, IS with the subscript 1 should be equal to IS with the subscript 2 equal to IS with the subscript 3, or this will just be simply equal to IS. We'll just represent that as IS because the three currents are actually balanced. So whatever current we could compute from the first one, it should be the same as on the second one, same on the third one, and we'll just call it IS. Okay, for simplicity. Letter C, the KVA rating of each of the two transformers. Two transformers meaning we are given a teaser transformer and a main transformer, and the problem is just asking what will be the load carried by the main transformer and teaser transformer. Oh, this is just an easy one because whatever load on the secondary, okay, we will divide it by 2, and that will be the load for the teaser and main transformer. Okay, we'll go to letter C now immediately. So the KVA per transformer, meaning per main transformer or teaser transformer, they should be I solved first letter C. It should be the kilowatt over power factor. Kilowatt over power factor is actually KVA. Okay, the total kilowatt delivered to the secondary is 130, so this 130 over 0.866. That will now be the total KVA of the entire system. But since we are talking two transformers and they should subdivide the load equally, this is times 1/2. So the KVA per transformer is actually 75 KVA. So the teaser transformer will carry 75, and the main transformer will also carry 75. This 75, this 75. Okay, let's try to go to the solution of the primary currents. What will be this current IP here considering the teaser winding? And what will be the IP current here, considering the main winding? This is the main winding on the primary side. This is the teaser winding on the primary side. So we'll do this part first, right? We are given the voltage on the teaser part. It's 2300, right? To bring out the solution, will just be, it's the same as an AC circuit, that is, hold on. Volt ampere is actually the product EI. And if we try to compute for current, it should be volt ampere over E. So we will be using this equation to compute for the current here. We know the load carried by the teaser winding, right? We know the applied voltage to it. So we could compute for the current by using this equation here. Okay? Considering the primary side and teaser winding, the KVA is actually 130 over 0.866 times 1 half. And this is actually 75. And this is actually solution letter C, 75. So we needed the 75 kVA and the computation of the current. The load carried by the teaser part is 75 kVA. So the current IP now on the teaser will be I sub P. It will be the load carried by it, which is 75 kVA. Converting this to volt ampere, this is multiplied by 1000. The voltage across it is 2300. So 75,000 divided by 2300 will be 32.6 amperes. This is 32.6 amperes. Considering again the primary side, but we will consider the main winding. We are now through with the teaser winding. Teaser winding is actually the winding that contains the 86.6% tap. If the tapping is 50%, that's the main winding. So we'll go now to the primary side main winding. Again, by using this formula, right? The total total current on the primary, considering the main winding, will be designated by I sub P also. The total load carried by this is still 75 kVA. So this should be 75 times 1000 over 2300. And still, it will still be equal to 32.6 amperes. Okay. There's another solution for this one. If you don't want to compute for the total current passing here due to 50% tapping and 50% tapping, you just take 1 half of 75. But for the voltage, you divide it also by 2. So it's the same as by using 75 times 1000 over 2300. Okay. We will use 75 over 2. That's 1 half. The kVA carried by the 50% tapping is 75 over 2 times 1000 as another solution. And the voltage should be, since this is 2300 and they are in phase here, the voltage per 50% is actually 1 half of 2300. So this should be 2300 all over 2. Okay. There is an over 2 over here. There is an over 2 over here. Actually, these two here cancel with this. Anyway, the operation is multiplication. So it will still be the same 75 times 1000 over 2300. 75 times 1000 over 2300. So it will still be 32.6 amperes. So by computing the current 50% and 50%, it will be 32.6. And if you try to compute for the current by using just one winding, but there is a divisible by 2 over here, and so will here. Like what I said, it cancel out, so it will come out just still 75 times 1000 over 2300. This is still 32.6 amperes. Okay. So in here, there is a current here, 32.6 amperes. In here, there is a current 32.6 amperes. This one. Oh, they are just single phase, so it will be two phase, right? So it's an easy one. There is no square root of 3 because it is single phase. Single phase, single phase. One phase, it's two phase. That's why it is two phase to three phase. Right? For the current on the secondary side, there's no problem. It's balanced. The current going out to line number 1, line number 2, and line number 3 are all the same. Like what I said, IS1 will be equal to IS2 equal to IS3. This is IS sub 1, this is IS sub 2, this is IS sub 3. And I put that as just simply IS without any subscript. The subscript is just S, no more 1, 2, 3 because they are all equal, right? And since the load on the secondary is three phase, we can use this equation here. For a three phase balanced three phase load, the total true power is actually square root of 3. The product of voltage line to line times the line current times power factor. Right? We are given P total. We are given the line to line voltage, it's 460. Right? And we are given the power factor. Power factor is 0.866. So we could compute for I sub L, and this I sub L will just place that as simply I sub S, which is equal to IS1 equal to IS2 equal to IS3. So the currents on the secondary side and all the lines are the same. And if we try to compute IS now by using this formula, we'll compute for I sub L. It should be P total over square root of 3, the product of voltage line to line times power factor. 130 times 1000 square root of 3 times 460 times 0.866. The secondary line currents, which are all equal in each line, is 188.41 amperes. Okay, we do not have any problem with the value of IS1, IS2, and IS3 because the load is balanced, so we could use the formula for a balanced load. And luckily, the currents in each line are actually equal, and it came out as 188.41 amperes. Okay, that's it, guys. That's how we compute currents for a two-phase to three-phase. We'll consider this one as single phase, it's two-phase. So in the computation of the currents here, it's an easy one. No square root of 3. It will just be simply, we will divide just simply the apparent power by the voltage across it. But on the secondary side, since it is three-phase, there is a factor of square root of 3. Okay, this is Professor David J. De Los Reyes. Good morning from Los Angeles.